Swayam Prabha. Digital India. Educated India.
Dear all, we are going to discuss Unit 2, this more interesting topic for mathematics for cyber security. Already we come across the topics are fundamental ideas, counting principle and mathematical induction, and these are all the ideas will be helpful to understand the number system and number theory. Number theory is a branch of mathematics which deals about the numbers in number theoretical aspects, and then we have a lot of subtopics. Then we have to understand how the number pattern is working, and based on the number patterns we are going to use in cyber security. In number theory, we are going to discuss elementary number theory. Elementary in the sense as here we have to discuss the elemental ideas of the numbers or fundamental ideas of the number ideas. So, these are all the things we are going to discuss, and particularly number theory is a queen of all mathematics and mathematics is a queen of all sciences. Therefore, it is more helpful and it is more interesting and useful in real time problem. Now, we are having a content of Unit 2 consists of introduction to divisibility, examples division algorithm. We are going to discuss only the statement and not go into the proof, and wherever we require the proof only we are going to discuss, and fundamental theorem of arithmetic based on the introduction and example, definition of greatest common divisor and least common multiple of two integers, and relatively prime numbers and other examples related to this. This is the 14th module. Like that we have a 15th module, introduction to Euclid's algorithm and based on the example, and then we have to extend the Euclidean algorithm and related to examples and problem, and more problems on Euclidean algorithm and extended Euclid algorithm in the following module. And then 16th module we have to discuss arithmetic function, multiplicative functions and completely multiplicative functions, and we use the book Song book, the element number theory by Song. That is, we have to understand the definition from that book, and based on the definition we have a theorems, and we have to need only the statement of the theorem, and based on that we have special functions, right, mu of n, sigma of n, tau of n, phi of n, s of n and phi of x, and related to examples. Based on that we have a lot of theorems from the Song book, and we need only the statement. Sometimes I will give the proof, and then followed with that we have a lot of definitions, and based on the Fermat-Little theorem and converse of a Fermat-Little theorem and Wilson theorem and so on, and followed with the module 20 is Chinese remainder theorem, and then with more examples of Chinese remainder theorem, and 21 module states that introduction to prime numbers, and Euclid proves infinitely many prime numbers, and 22 states that solving the primitive root of a number and primality testing using Euler's theorem, Fermat's theorem and Wilson theorem, and followed with the models, problems and miscellaneous exercise, and we are finally applying to the cryptograph. So, these are all the contents we are going to discuss. Let us start with the interesting topic of foundation of divisibility. Let us start with definition 1. Let a and b be two natural numbers. I hope natural numbers is a number. We start with 1, 2, 3 and so on n, right. So, this is the natural number such that b leaves a remainder 0 upon division by a, then b is said to be divisible by a. So, we denoted by a divides b. A divides b in the sense that b by a. Sometimes the notation b is to a is nothing but b by a is also used, but in this note we shall make the most common use of notation is a divides b. So, keep it in mind this notation, so that the rest of the definition problem you can understand yourself. Here, A is called a divisor of b and b is a multiple of a. If b leaves a remainder other than 0, then b is not divisible by a and is denoted by a does not divide b. So, keep it in mind this statement. We have an example. You take 343 divided by 7 and 565, 655 is and so on. So, these are all the ways we can give the example of divisibility, one divides other. Now, for the definition 2, if any positive integer, I hope already discussed n is a natural number, right, and then we have a whole number, start with 0, 1, 2, 3 and so on, n, it goes to infinity, here 1, 2 and so on, n, and then we have a integer I or z, start from minus infinity and so on, minus 3, minus 2, minus 1, 0, 1, 2, 3 and so on, infinity. So, this is the meaning of integer. If any positive integer is not divisible by any positive integer except 1, and that number we call the special number is a prime number. So, prime number mean divisible by itself and 1. So, alternatively we can write prime number is divisible by itself and 1. So, keep it in mind this, we can understand the beauty of the prime. Other than the prime is said to be composite. So, 2 is a prime, 3 is a prime, 5 is a prime, 7 is a prime, whereas you take 4, 4 is product of 2 primes, therefore, it is called as composite. So, it is called as prime numbers. I hope you can understand what is the meaning of prime and composite. So, prime number is the most useful in number theory, right, and it is the block builder of entire number theory. For example, 2 is the only even prime and even prime is greater than 2, then it must be divisible by 2, thus it cannot be prime. So, first 3 odd primes are 3, 5, 7. Next definition, if a number leaves a remainder 0 upon division by 2, then it is called as even. You take 2 divided by 2, right, 2 divided by 2. So, the remainder is 0, therefore, 2 is a even number. Like that you take 4, 6, 8 and so on. So, if it leaves the remainder 1, then it is called as odd. So, I hope you can understand the definition of even and odd. Suppose if you divide by 2, 3 divided by 2, 1 times of 2, remainder is 1, therefore, 3 is odd. So, like that we can define even number and odd number. So, the property of a number being even or odd is called it as parity. So, two numbers are of same parity if they both are odd or both are even. Otherwise, they are of opposite parity. In other words, two numbers give same remainder upon the division by 2, so they are the same parity, else it is opposite. So keep it in mind this statement, so that you can understand what is the meaning of parity. For example, you take 5 and 7 of the same parity, whereas 4 and 3 are not same parity. Therefore, check the truth of the following claims. The sum and the difference of two numbers of same parity is even. The sum and difference of two numbers different parity is odd. Increase or decrease a number by a multiple of 2 does not change the parity. Any odd multiple of a number has the same parity of the number, and even multiple has a parity even. So, every number is divisible by 6 is even, but converse is not true. So, every even number is divisible by 6. The first claim is true, whereas the second is not true. So, it is not a if and only if statement. And check the following claim: every even number is divisible by 2 is an if and only if 1. For this notation, if and only if is used. For the example above, x is even if and only if x is divisible by 2. So, the parity remains unchanged after rising to a power. Next, the divisibility issues. If two numbers are of same parity, then the difference is divisible by 2. The number is divisible by 3 if and only if the sum of the digit is divisible by 3. For example, you take a 15, you take for unit digit and 10th digit is 1 plus 5 is 6, 6 divided by 3, therefore it is divisible by 3. The number is divisible by 4 if and only if the number formed by the last two digit is divisible by 4. Say for example, you take 10,024, the unit digit is 4, 4 is divisible by 4, therefore it is divisible by 4. And as well as you last two digit, you take it 24 is divisible by 4, therefore it exactly divisible by 4. So that is the meaning of the last two digit, you take it and then pakka it works. A number is divisible by 5 if and only if the last digit is 5 or 0, check it out, definitely it divides. So you have 55,575 and 100. You see the last digit is 0 of this 100 and the last digit of the 55,575 is 5, therefore both are divisible by 5. A number is divisible by 7 if and only if the difference of two numbers formed by the separating the last 3 digit, the rest number of is divisible by 7. So example 2401 is divisible by 7 because 401 minus 2 you take it, so that 399. 399 can be written as 7 into 57. So this number is divisible by 7. So like that we have to do the statement of divisibility of 7. So a number is divisible by 8 if and only if the number formed by the last 3 digit are divisible by 8. For example, 5512 is divisible by 8 because 512 is divisible by 8. So this way we can express the sixth statement. A number is divisible by 9 if and only if the sum of its digit is divisible by 9. For example, you take 3, 4, 5, 6, so is divisible by 9 because 3 plus 4 plus 5 plus 6 equal to 18, 18 is divisible by 9. So a number is divisible by 11 if and only if the difference of sum between the odd position digit and even position digit is divisible by 11. For example, 121, 341 you take it. So this is odd, this is even, this is odd, this is even, this is odd, this is even. So these are all the position. So odd position you take it, even position you take it, and then odd position is 1, 1, 4. 1, 1, 4, 1, 1, 4. even position is 2, 3, 1. So, add them. So, it becomes 6, right, and then this becomes 6, 6 minus 6 is 0, and if it comes like that, then definitely it is divisible by 11. Now, we are going to discuss the properties of divisibility. It is more interesting and helpful to understand the next topic, division algorithm, extended Euclid division algorithm, and so on. So, you should be thorough in these ideas of the divisibility, so that you can understand further congruences and so on. If A divides B, that is B divided by A must be a positive integer. So, let B divided by A is equal to K, therefore, B can be written as AK. So, if A divides B, there exists a unique positive integer. In fact, it is a quotient of the division of A and B, such that B equal to AK. So, also note that the relation K divides B is true. Obviously, A divides A is true, and A divides 0 is also true for all A in Z. If A divides B, then A divides minus B, or A divides minus of A divides B, or minus A divides minus B also true. If A divides B, of course, B greater than or equal to A, like that you have to assume, then only it will be clear. If B equal to A is also exactly divides, but the B less than A does not do that. Since every factor of A must be included in the factorization of B, therefore, B must be greater than or equal to A. The only possible case is when B less than A is B equal to 0, especially if A comma B in N and A divides B, then B is greater than or equal to A. If A divides B and B divides A, then easily follows that the statement of 3 that A equal to B must be hold. If A divides B and B divides C, definitely A divides C, right, is also true. So, 2 divides 3, 3 divides 6, definitely what 2 divides 6. So, this will be true like that. So, let B equal to AK and C equal to BK dash, and substitute B equal to AK in this equation. So, that C equal to AKK dash, which implies K into K dash is a constant, therefore, A divides C. If A divides B, then AC divides BC too, and the converse is also true, that if AC divides BC, then A divides B. So, this is straightforward, that if AC divides BC, therefore, BC by AC equal to B by A is a positive integer, or A divides B. So, if A divides B and A divides C, then any combination of B and C is divisible by A, otherwise A divides Bx plus Cy for integer x and y. So, the important cases are A divides B plus or minus AQ, and A divides B plus or minus C, and then A divides B plus or minus A. So, if D divides P, then D equal to 1 or D equal to P. So, if A divides B, every prime divisor of P of A also divides B. So, every prime divisor P of A is also divides B, right. So, next followed with Euclid lemma. So, the Euclid lemma says that if P is a prime such that P divides AB, then P divides A or P divides B. So, if A does not divide B, then it must leave a remainder other than 0. So, it is call it as some R say, then P minus R would be divisible by A. For example, if having what P exactly not divides, then P equal to this Q is a quotient, A is a divisor, B is a divisor, and B is a dividend, and then we have a remainder, Therefore, AQ plus R which is equal to B. Rather, we can write B minus R equal to AQ. So, this way we can write the dividing one terms to the another. Now, we prove that R is a unique positive integer and R should be lies. So, this condition is true when less than or equal to E. So, this condition is true when R equal to 0 exactly divides. If R is more than 0 and R is less than A, then we have to do what? The further divide one another. For the sake of contradiction, suppose that we have a 2 divisor AQ1 plus R1 equal to AQ2 plus R2 with R1 R2 is less than A, then we have a what subtract together. Therefore, AQ1 minus Q2 equal to R2 minus R1, and this implies A divides R2 minus R1, but R2 minus R1 less than A is a contradiction, implies. So, only unique way we can express B equal to AQ plus R. For all composite n greater than 1, n has a prime divisor P such that P is less than or equal to root n. Assume that the smallest prime factor of n is P, then n equal to Pk for some k greater or equal to P. If k is less than P, then k would have at least one prime factor less than P, but it is not possible. Therefore, k greater or equal to P implies n equal to Kp is greater or equal to P square, implies P is less than or equal to root n. So, using this property, we can determine whether a number is a prime or not. Though this is not an efficient approach at all, it is very useful for small numbers. Now, we are going to discuss the fundamental theorem of arithmetic. The fundamental theorem of arithmetic is every positive integer can be written uniquely as a product of prime, with the prime factor is in the product written in the order of non-decreasing size. For example, the factorization of the some positive integer are given by 240 can be written as 2 into 2 into 2 into 2 into 2 4, 4 into 2 8, 8 into 2 16 into 3 into 5. So, we have what 2 power 4 into 3 into 5, right. So, this way we can write what 240 like this. And similarly, 28 can be written as 17 into 17 which is equal to 17 square, and then 1001 can be written as 7 into 11 into 13 and so on. So, this way we can do with the help of splitting of the composite number into prime powers factors, and then that is the meaning of fundamental theorem of arithmetic. So, that is every positive integers can be written uniquely as the product of primes, and this prime factor is a product written in order of non-decreasing size. So, we have to note that to combine all the factors of a particular prime into powers of this prime, such as in the previous example. Therefore, for the factorization of 240, all the factors of 2 were combined to form 2 power 4, factorizing of an integer in which the factors of primes are combined to form powers are called prime power factorization. Okay. So, keep it in mind this we have to go further. Now, we have a lemma: if A, B, C are positive integer such that the GCD of A comma B is 1 and A divides BC and then A divides C. So, that we have to understand the first statement, that is you take A as 2 or 3 whatever may be, right, So 2 comma 3, the GCD of this number is 1, and then you take C is another positive integer, let it be 5. So this is A, this is B, this is C, and then you take E2, and you have to take 3 into 5, it becomes 15 by 2. So 2 does not divide 15 implies 2 does not divide 5. So it holds good in other way. So this way we can write what the part of this. So suppose you take A equal to 2 and B equal to 3, and C is not necessary the GCD of one of these numbers, therefore C equal to 6, you have to take it. So what happens? 2 divides 3 into 6 implies 2 divides 6. So that is also true. So keep it in mind these ideas. We have to go further corollary. If P divides the product of numbers A1, A2 and so on, An, where P is a prime and A1, A2 and so on, An are integers, then there is an integer I such that 1 less than or equal to I less than or equal to n, such that P divides AI. So if P divides, P means you take 2, 2 divides product of the numbers 2 into 3 like that, right, to 5. So where P is a prime and these numbers are a positive integer, then in between one number I may be 1 or I may be n or I may be in between them. So here definitely among all these one of the numbers is 2, definitely 2 into 3 into 5, it divides 2. So this total number is divisible by 2. So this is the meaning of the corollary, that we have to go to the further analysis. For example, the positive divisors of 120 can be written as 2 cube into 3 into 5 are those positive integers with prime power factorization containing only the primes 2, 3, 5 to powers less than or equal to 3, 1, 1 respectively. So the these divisors are, for example, you take 1 and 2, 2 square is 4, 2 cube is 8, and 3 is 2 into 3 is 6, 2 square into 3 is 12, 2 cube into 3 is 24. Therefore, here these 3 numbers divide by 3, and 5 you take it, and 2 into 5 is 10, 2 square into 5 is 20, and 2 cube into 5 is 40. Therefore, prime power factorization containing the primes 2, 3, 5, then less than or equal to 3, 1, 1 respectively, like that coming, right. So 3 into 5 is 15, 2 into 3 into 5, so 2 cube into 3 into 5 equal to 120. So this way we can do that, what, the divisibility in terms of the primes and composite, and the P divides the product of the integers, and definitely one of the numbers of prime is divisible of this composite number of product of the primes powers. In general, to describe the prime factorization, to find the GCD of the divisors, common divisors, let A comma B minimum, right, and denote the smaller or minimum of the two numbers A and B. So let the prime factorization of A and B as A equal to like that and B equal to like that, where each exponent is a non-negative integer where all prime occurring. In the prime factorization of A and B are included in both product, perhaps with 0 components, we know that the GCD of A comma B equal to these primes like that. Since each prime Pi A and B share exactly minimum of ai comma bi factor of pi. That is, you take A as a product of primes 2 into 3, right, and B as a prime which is product of 5 into 7. Now, the minimum of A comma B, right, minimum of A comma B is what? That is 2 and 5, right. So, you have to take the common factor of this one, 2, right, 2 into 3 and 5 into 7, we have what minimum you have to take it. Then they are include both P1 of minimum of A1, right, and A2, B2 and P1 A and Bn, so that we have what AB will come. So, A is 6 and B is 35. So, you have to take the minimum is 6 and then the product will come like that. Okay. So, you have to take a minimum of this you have to take it A1 B1, right, and A2 B2, A3 B3 and so on. So, this is called it as what here P1 is equal to 2 and P2 equal to 3 of this, and for here for this is corresponding to A, and for B we have to take what B1 is 5, right, that is P1 is equal to 5, P2 equal to 7, and here you have to minimum of 1 1. So, A1 all are equal, therefore 1 1 only will come. A1 is also 1, A2 is also 1, B1 is also 1, B2 also 1, therefore here no issue at all. Therefore, then the resultant will be the same, will come like P1, that is 2 power 1 and 3 power 1 into 5 power 1 into 7 power 1. So, 6 here 35 and same will be whole screw. You take it differently for what higher power prime factors, so that the different types of the power factors will come. So, like that we can write the what the two numbers of A comma B can be written as product of primes, and then we can write like this.